Okay, so now that we looked at the H matrix, and you can see that it tells you how things stretch and rotate line by line. Now we want to separate all the stretching and deforming terms, shape change terms from the rigid body rotation terms. Okay, the way to do that is we break up H into symmetric and anti-symmetric parts and separate shape change from rigid body rotation. Okay, let us see how we can do that. Okay, so here's the picture on the right hand side showed what happened to a given H matrix. So remember our H matrix looked like this: 0.1, 0.06, 0.1, blah, blah, blah. We saw that already. Every entry of H must be small. Correspondingly, the deformation looks like this. Okay, on the picture, you can see the red line moves a little bit. Now everything is moved only a little bit, not a lot, because H is small. Okay, so we want to find the axial or length change and shear angle change strains. This is what we want to find. So how do we do that? So we first find the strain matrix as the symmetric part of H, that is E equals 1/2 H transpose plus H. You take H, add to the transpose to it, and you do that. So you will get E, first row of E is 0.1 minus 0.02, 0.04. Second row is minus 0.02, minus 0.02, 0.025. Last row is 0.04, 0.025, 0.05. Notice it is symmetric. So we have to interpret 6 terms. We'll show you what we mean. The first term, diagonal terms, approximate the change in length per unit length. It's exactly the same as in H. We already discussed this. So E11 equal to 0.1 means the X line element becomes 10% longer. E22 equal to minus 0.2 means 0.02 means that the Y line element becomes approximately 2% shorter. E33 equal to 0.07 means the Z line element becomes approximately 7% longer. Note that even these things, which are quite small, are much too large for metals. Mostly for metals, they are in the range of 0.1%, not even 1%. Or even 10%. They are 0.1% or smaller. So that is why this kind of small displacement gradient version works very well for us, even though it's approximate. When the displacement gradient is small, we want to look at the angle changes. So here is H, here is E, and I will show you how the angle change works. The off diagonal terms approximate the change in angle between the two line elements. It's called 2EIJ equal to gamma ij. That's called the shear strain, gamma ij. Eij is called the tensorial shear strain. And the two comes from the fact that we are going to do some averaging instead of adding the two terms. So 2E12. So you remember E12 is minus 0.02. So 2E12 is minus 0.04, means that the angle between the X and Y fibers increased by 0.04 radians, which is 2.3 degrees. So you can see that they get spread apart. So that's negative. Okay, 2E13 equal to 0.08 means that the angle between the X and Z fibers, one is X, 3 is Z, remember? So X and Z fibers decreased by 0.08 radians, which is 4.6 degrees. And the angle between the Y and Z fibers decreased by 0.05 radians, which is 2.9 degrees. Note, since each component of Hij shows which way each line element rotates towards the other coordinate axis, the sum of them measures how they move towards or away from each other. That's what we are using. You see what I mean? Hij plus Hji. So that's what we are doing. Okay. So that's the idea. Okay. Very good. So now that we did that, we now need to do rotation matrix. So I'm given the small deformation matrix. We will need the right hand rule for explaining all of these things. I'll show you what I mean. We want to find the rigid body rotation. So we first do the anti-symmetric part of H now. We did the symmetric part previously. Now we do the anti-symmetric part. What we mean is H minus H transpose. Instead of doing H plus H transpose, we do H minus H transpose multiplied divided by 2, and we will get 0. The first row will be 0, 0.08, 0.06. Second row will be minus 0.08, 0, 0.025. Last row will be minus 0.06, minus 0.025, and 0. So notice that this anti-symmetric matrix, that is every off diagonal term is the opposite of the corresponding version. You see what I mean? So We will start in a very peculiar way by starting with W23, which is 0.025. What it means is that the line elements rotate by 0.23 to 0.25 radians in the YZ plane. 2 is Y, 3 is Z. So in the YZ plane, which means it's rotating around the positive x-axis because it goes from Y to Z. Right? That's where we use the right hand rule. Okay, so the whole body, the whole element rotates by about 0.025 radians as a rigid body around the x-axis. W13 equal to 0.06 means that the line elements rotate 0.6 radians in the XZ. W13 is X is 1, Z is 3. But XZ, if you look at it, is a negative y-axis. So if you want to look around the positive y-axis, it is minus 0.6 radians. So you have to be careful about the sign. W12 equal to 0.08 means that the elements rotate by 0.08 radians in the XY or 1-2 plane, i.e. around the x-axis. Sorry, around the z-axis, because XY is 1-2. Okay. So that's how it works. I should say the z-axis is the last one, and that is how we look at the rigid body rotations by looking at this W matrix. Thank you very much.